So that takes us to slide 25, next new slide. That other previous slides were just working out the problem. I had done it all on one page. We come up with a Henderson Hasselbach equation, which is even easier to calculate buffers. A very unique equation that allows us to calculate quite readily the pH of a buffered solution. The equation says that we can calculate the pH of a buffer knowing the pKa. That's just negative log of the Ka value, that P is just negative log, and the initial concentrations of the weak acid and the salt. Check. As long as the X is small, the approximation is valid. Mental note is just saying it has to be less than 5% dissociation to make the math valid, so 5% rule. pH can be found by taking the pKa plus the log of the ratio of the base over acid. And notice what makes this unique? We're tossing out X anyway, so why bother to do the ice chart? Take the values from the initial conjugate pair and plug that into the Henderson Hasselbach equation. pH is equal to pKa plus the log of the ratio of base over acid. It's the initial line from the ice chart. Leave that equation handy. Let's take a peek at an example. This is quite busy, so I'm going to take the Henderson Hasselbach derived and just kind of show it on the next slide. Grab a sheet of paper. I'm going to cover up what we know. What is the pH of a buffer? As soon as I read buffer, I think Henderson Hasselbach equation. I have a weak acid, H, C7H5O2 with a conjugate base, common ion effect here. This is a salt giving us a buffered solution. So let's write this out, and I'm going to use generic chemistry. HA is in equilibrium with its acid ion and the negative. The anion and the weak acid are a conjugate pair. The concentration of the acid, and again I can write ice chart, but we're only using the initial value, is 0.05 molar. We're tossing out the fact that it dissociates at all because it does so insignificantly that this part becomes irrelevant for Henderson Hasselbach. So just think of this as a straight ice chart, but only row 1. The initial amount of the acid, relatively small, 0, and the base itself is coming from the source of this, the salt, 0.15 molar. Alrighty. Henderson Hasselbach says pH is equal to pKa plus the log of the ratio of base over acid from the initial amount. No ice chart. I do need to know a Ka or a pKa, and that one I don't have memorized, so I'm going to have to peek ahead. It tells us right here a Ka, so I'll take it. These are provided for us in our chart. So Ka value 6.5 times 10 to the negative 5th. All right, I need to know that before I can solve. So pH is what we're solving for. Now we have Ka. I looked it up either by cheating and looking in the example, or really in my textbook. There's a whole chart of Kas for various acids. I'm going to take the negative log of 6.5 times 10 to the negative 5th. That's the pKa, plus the log of the ratio of base, 0.115, over acid, 0.05. pH is negative log of Ka, that's the pKa part, plus the log of the ratio of base over acid. Let's get a common answer, and then check our work. Let me get the calculator on the screen. We get negative log of 6.5 e negative 5, close parentheses, plus the log of the ratio of 0.15 over 0.05, close parenthesis, equal. pH is 4.66 pH units. Negative log of Ka is pKa plus the log of the ratio of conjugate base over the acid. Gets us 4.66 pH units. Much easier than an ice chart. Let's see. Oh, 4.66. I was trying to see. There's a lot of writing on here, but we did get it right. 4.66 comes out to be the answer. So again, validates our 5% rule. Let's try another. What's the pH of a buffer that has an initial concentration of 0.14 molar in acid and 0.071 molar in its conjugate base coming from the common ion here, the salt potassium fluoride? pH can be found by taking the pKa given to us directly, 3.15, plus the log of the ratio of base over acid. The base, 0.071 molar, over the acid, 0.14 molar. We'll hit that Henderson Hasselbach and have the pH. 3.15 plus the log of the ratio of 0.071 over 0.14. Close parenthesis. pH here, 2.86 pH units. Let's take a peek, see if we got it close. 2.86 pH units. The Henderson Hasselbach just makes the calculating pH a lot easier than an ice chart. Okay. So Henderson Hasselbach equation is generally good enough when x is quite small. In other words, less than the 5% rule. The x is small approximation will work when both of the following are true. The initial concentrations in acid and its conjugate base are not very dilute, and the Ka is pretty small. So for most problems, this simply means the initial acid and its salt should be over 100, even better would be over 1,000 times larger than the value of Ka. 90% of the time they are. Let's catch up to a new spot. Alrighty. How much does the pH of a buffer change when an acid or base is added? And it just says, though buffers do resist change in pH, when an acid or base is added to them, their pH does change somewhat. We do consume and produce acid and base ion. Calculating the new pH after adding acid or base requires breaking the problem into two parts. Number one, stoichiometry, our favorite word. We do a stoichiometry calculation for the reaction of added chemical with one of the ingredients. Added acid reacts with the base to make more acid, or the base reacts with acid to make more base. Think about that bar graph we drew together separately from the PowerPoint. Add more acid, you make acid. Add more base, you make more base. I do the stoichiometry first, followed by the equilibrium calculation to pull out hydronium to get the new values of the pH. Stoichiometry first, followed by Henderson Hasselbach. Let's take a peek. What's the pH of a buffer that has 0.1 mole of an acid, acetic, 0.1